We're going to talk about basically matter. We're going to talk about different states of matter. We're going to talk about physical changes, chemical changes. We will also talk about mixtures and all that good stuff. So let us get into it. So when we talk about matter, matter is really anything that basically occupies space and has mass. And really, when we talk about matter, a lot of times we do focus on really the different states of matter. There is the solid state. And in the solid state, everybody is pretty tight to one another. They're packed in there pretty good. We also have the liquid state, where they're still relatively packed in pretty close to one another, but there's a little bit more room for movement. They're able to sort of pass one another. That's why when we think about liquids, right, they are fluid. We could pour them and stuff like that. You can't really pour necessarily a solid. It all just falls as one. In the last sort of state of matter, we have gas. And in the gas state of matter, pretty much everybody has broken apart from one another. They're flying around. They're causing collisions with the container, and that causes pressure as they kind of hit the containers. So a lot of what we look at in chemistry is sort of these different states, how they change from one state to the next. A reminder that a couple changes of state, when we go from solid to liquid, that is the process of melting, right? Like if you took an ice cube out, it would start to melt. As we go from liquid to solid, that's the process of freezing. Yeah. If we go from liquid to gas, that's the process of evaporation or vaporization. Going from gas back to liquid, that is the process of condensation. As we go from solid, skipping the liquid part and ending there at the gas part, that is what is known as sublimation. And lastly, as we go from the gas part, once again, skipping the liquid part and ending up there in the solid spot, that is what is known as deposition, like you're depositing something on it. Now, when we talk about these processes of melting or freezing, does melting and freezing occur at different temperatures or the same temperatures? If the melting and freezing occurs at the same temperature, actually. So these things do occur at the same temperature. It's what is sometimes referred to as the normal melting point or freezing point. So melting point or freezing point there of a substance. So for example, water at exactly 0 degrees Celsius, that is where it both freezes and also melts. So exactly at 0 degrees Celsius for something like liquid water or water, thank you. You basically have both phases happening at the same time. So you got like ice crystals. So you got some solid, you got some liquid occurring at say 0 degrees Celsius. It's not until you get a little bit above 0 degrees Celsius that you really do get sort of liquid. It's not until you get a little bit below 0 degrees Celsius that you actually have solid. But right there, exactly at that 0 degrees for water at the melting point and freezing point, you basically got both phases sort of happening. Same thing happens here, the process of evaporation and condensation. It also occurs at the same temp. That is what is sometimes referred to as the normal boiling point of a substance. Boiling point. And once again, that does happen at the same temperature. So for example, using water again, that's 100 degrees Celsius where that occurs for water. So exactly 100 degrees Celsius, You have basically some liquid water. You also have some steam or gas coming up, which is water vapor coming off of it. So it basically happens at the exact same temperature. It's not until you get a little bit again above that 100 degrees Celsius that you really do transition fully into the gas phase. Not until you're a little below that 100 degrees that you're again back in the liquid phase. Any questions on that there? Now, we also will talk about in the next chapter we discuss as well, but there is energy associated with doing these processes. So as I go from solid to liquid to gas, do I need to put energy in to do that or take energy out to do that? So if you go from solid to liquid to gas, you need to, if you take an ice cube out, what happens to it? It starts to melt because it is gaining energy, right? So you take liquid water, you want to make pasta, you put fire underneath it, right? It starts to boil, right? You create gas basically. So that all requires energy to be put in or energy to be absorbed. And as we'll talk about more in the next chapter, that is what is referred to as a endothermic process. And it is opposite as you head the other way. If you go from gas back to liquid, back to solid, we have to really release energy in these cases. So if you think about gas molecules, which are flying around, if they lose energy, they're not flying around as fast. And when they actually come in contact with other gas molecules, they no longer have enough energy to completely escape each other. So they kind of clump and drop into the liquid phase. If you continue to remove energy at that point, they will continue to kind of come together because they really can't start passing each other or anything like that. And they'll go into the solid stage. So as we do those processes in that order, energy is released. And that is what is referred to as a exothermic process. Any questions on any of that there? Go that way. So as I mentioned, matter is basically the stuff that the universe is composed of. It does pretty much have mass. It occupies space, and obviously that's pretty much everything or most things. So as we just talked about, there are the three states of matter, which is important. Solid, things like wood, bone, steel. Solid things have a definite shape, and they are difficult to change. They're sometimes referred to as being rigid. Clearly, this tabletop is a solid. It's not that easy. I can't just fold it over, right, and change the shape of it or anything like that. So it's very difficult to do. Liquids like water, gas, do not have a definite shape, but they do have a definite volume, and they will take the shape of whatever container you put it in. So what that means is obviously if I had 10 milliliters of water and I had it in a cup, it would take the shape of the cup. If I took it through the trash can over there, it would take the shape of the trash can. If it was one of those silly straws, right, it would fill up the silly straws the way the shape is. What it means is that it has a definite volume is if you started with 10 milliliters of water and you like moved it from one container to the next and you're not a klutz and spilled it anywhere, you should still have 10 milliliters of water all the way through as you transfer it from one spot to the next. Gas, on the other hand, things like air or gas, they take the shape of the container and they fill it uniformly. So the idea with gas is they are flying around, so they are completely filling the actual container uniformly as they're moving around. That's something we'll talk about when we get to the gas chapter. That's something that deals with ideal gases. One of the ideas of ideal gas is, really the volume of the gas is the same as the container because it's flying around and really filling the entire container uniformly. So here's obviously some liquid in different containers and obviously taking the shape of it. Here's the three states of water. Again, that is ice, liquid water, and gas or steam. And as we might have talked about before, water is an unusual substance as the solid version here, as we talked about, is actually less dense, right? than the liquid version. And you can see that in this picture as the water molecules come together and they really bond with each other. It creates all these open areas in the water molecules. And again, if you think about, as we talked about with density, which is mass over volume, that's going to increase the volume and thus will decrease the density of solid water versus obviously liquid water, where you can see they actually get, because they have enough energy, a little bit closer to one another. They're able to move around. So it's a very unusual sort of characteristic. As we talked about, most things are actually more dense in their solid state than in their liquid state. So water is a little exception of that. But as they lose energy and they start hydrogen bonding, which is what they're doing here, they kind of keep a pretty good distance from one another. And that creates all that open sort of space between them. Any questions on that? And obviously in steam, when we start to boil and we see the steam coming off, that is our water molecules that are bouncing around, obviously, and creating pressure. Now, the state of the given matter does depend on really the forces that hold it together. So we'll talk about this in a later chapter, but the idea here is there are some forces which are referred to as intermolecular force. And that's basically the force that holds two molecules together. So for example, if you had a water molecule like we were looking at, it is the force between those two water molecules that basically hold it together. So that's what kind of keeps them there. For example, for water, if these were two water molecules, that would be what is known as hydrogen bonding, which is the force that holds it together. And hydrogen bonding is a relatively strong intermolecular force. So the stronger the intermolecular force, the most likely it will not be a gas in normal conditions. The weaker the sort of force that holds the molecules together, the more obviously it will be a gas in certain cases. For example, if we took something like methane, which is CH4, basically the stuff that comes out of your gas vent there in lab, right? When you light your Bunsen burner, clearly it's a gas. Methane is a nonpolar molecule and basically held together by a very, very weak intermolecular force. So the methane molecules together are held very, very weakly, which means it just takes not very much energy or stuff for it to just behave in the gas phase. The other thing that those forces will affect are things like boiling point temperatures, melting point temperatures. The weaker the intermolecular force, the lower the melting point and boiling point. The stronger the intermolecular force, the forces that hold the molecules together, the higher boiling points and melting points that you would expect to see. So things that are solid, as we talked about there, are rigid. They have that fixed shape. Our liquids have that definite volume, but takes the shape of the container. And again, gas have really no volume and no shape, but takes the shape and volume basically of its container. Any question on the different states of matter? So let's talk a little bit about physical properties and physical changes, and also chemical properties and chemical changes. So when we talk about a physical change, that is something that can be measured without really changing the composition or identity of a substance. Typical physical properties are things like odor, color, volume. Probably the most common sort of physical property we come across a lot in chemistry is the state, as we were just talking about. You know, is it solid? Is it liquid? Is it a gas? Things like density, melting points, and boiling points, those are all physical properties. Physical properties usually go with physical changes. And when we have a physical change, basically what we start with and what we end with are fundamentally the same thing. So when something goes through a physical change, really some type of physical aspect of it changes, but fundamentally what it is still the same thing. So for example, when we take our ice cube out and we let it melt or we heat it up or whatever it may be, when the ice cube melts, it becomes liquid water. And then if we took that water and we started to heat it up and boil it, it would go from liquid water to steam. All three of those things, the ice cube, the liquid water, and the steam, they're all H2O. Yeah. They're all water fundamentally. It has not changed to anything different. So when you do any of those processes, that is a physical change. And one of the important things about a physical change is, typically speaking, you usually could sort of kind of put back the original thing in a physical sort of method. But the main thing is, it is really what you started with is what you end with, may just look different. If you had a peanut or something like that, and you crushed it, they still are fundamentally peanuts. They just look very much smaller, right? And stuff like that. So those are all examples of physical changes. You know, if you had a piece of paper and you colored it red, it is still fundamentally still a piece of paper. It just looks red. So those are all physical type changes. And again, very common physical properties is what you see there: solid, liquid, gas, odor, color, melting points, and boiling points. Any questions on that there? So as I mentioned before, our block of ice, again, we could record the temperature where it starts to melt, and that would be a physical property. And again, the physical change there. If you wanted to, you could capture the steam, cool it back down, get the liquid water, take that liquid water, put it back into the freezer, and you would get back your ice. So again, it is fundamentally the same thing. There really is no chemical reaction that has taken place. It's just a physical sort of change that occurs. Now, that is different than a chemical property or a chemical change. When we talk about chemical properties are really the resistance or ability of something to go through a chemical reaction. So for example, a lot of chemical changes are what are referred to as chemical reactions, but in a chemical change, the important thing here is what we start with and what we end with are two fundamentally different things. So what we start with and what we end with are two fundamentally different things. The other important part of that is you cannot get back the original sort of substances by any type of physical means. So you can't freeze it, you can't boil it, you know, filter it and get back the original substances. So for example, when we take, say, hydrogen gas plus some oxygen gas and we get some water that is formed, again, you could do whatever you like with the water. You could boil it, you could freeze it, you can melt it if it's solid, but you will not get the hydrogen gas and oxygen gas back. Otherwise, when we would put water up on the stove to make pasta, there probably would be an explosion because you would have hydrogen gas and oxygen gas happening. So that doesn't happen. It has fundamentally changed to something different than what it started with, and we can't get back, you know, what it our original guys through any type of physical means. So physical changes, what we start with and what we end with, basically the exact same thing fundamentally. Chemical change, what we start with and what we end with are two fundamentally different things. And you can't really get back the original guys without going through another chemical reaction. So in order to get these guys back, we would actually have to do another chemical reaction where we would run an electrical current through it. And you could break apart the water into hydrogen gas and oxygen gas. We'll do it a little bit later on in a lab, I think. So you could actually see that. But you can't really get back the original components by any type of physical means. You have to do a chemical reaction. So chemical change is a chemical reaction. Evidences of chemical reactions. When you look at them, you see bubbles maybe form if you do something. Maybe a solid forms. Maybe there's heat and stuff coming off. These are examples of things that you could kind of recognize a chemical change happening. So as I mentioned there, the hydrogen gas burning and oxygen gas to form water. Once again, once you form that water, it's not going to really go back to hydrogen gas, oxygen gas without another chemical change. When we form something like rust, rust is basically iron and oxygen coming together. And when it comes together, it forms iron 3 oxide, which is rust. But basically at that point, the iron and the oxygen are now sort of bound together. And if you ever study something that's rusted, you can't kind of get back the iron by itself or the oxygen gas by itself by just trying to clean it, filter it, heat it. So it has really went through a chemical reaction here and changed. And again, that would be an example of a chemical change as well. Any questions on the difference between physical change, chemical change? And another example there, hard-boiled egg. Obviously, as you're cooking it, inside is going through some changes in their physical appearance and also the chemical appearance. And then clearly when we eat things, right, our enzymes and stuff take care of a lot of those things, break it down into other things that go through chemical reactions, and we can't get it back. So again, a summary of chemical and physical changes. Physical changes one or more of the physical properties, but no fundamental component is changed. Very commonly, it is those changes of state that we see are very common physical changes. Chemical does involve some type of fundamental change where a chemical reaction has occurred, and what you start with and what you end with are really two fundamentally different things. Silver tarnishing by the reaction. When you have anything that sort of oxidizes, right, and goes through oxidation, like metals or something like that you might have, that really is sort of a chemical reaction that's occurring. It's basically the oxygen and the metal coming together, and there's a change that really does occur in those cases. So let's talk a little bit about elements and compounds here. An element is a substance that cannot be separated into simpler substances by chemical means. So you could think of elements as sort of your like alphabet, if you will. It's kind of as far back as you could go, and different combinations of the elements give us different molecules or compounds. Elements are as far back as you could go. You can see them on the periodic table. There is where we have all of our elements listed. The simplest representation of an element is an atom, as we'll talk about in another chapter, but basically has protons, protons, electrons, and neutrons, right? We'll talk about. So basically every element's representation is an atom, which has those different parts. Now, some atoms or elements are made up of what are referred to as molecules. So some elements come naturally as basically two of them together. So things like hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine. These guys come as what are referred to as diatomic molecules. That is naturally how they come when they are by themselves and not combined with anything else. So something like hydrogen is basically two hydrogen atoms bonded together. Something like oxygen is two oxygen atoms bonded together. That is naturally how they come. Those are still elements, and they're also molecules because there's more than one atom together, basically, that is there. So each element is made up of a certain kind of atom. If you have a pure element, say of aluminum, it will only have aluminum atoms in it. And as I mentioned there, we do have those guys that you should know. That is naturally how they come as elements. So let's talk a little bit about a couple of things. When we do look at the periodic table, we'll officially talk about it, I think, in a later chapter. But basically, if you look at the periodic table, somewhere around boron, you usually will see like a staircase that sort of comes down. And really to the left and on the bottom couple of rows there as well, these guys, these are what are referred to as metals. And these are elements that are considered metals. Metals are good conductors of heat and electricity. They are usually shiny. They usually can be pulled into wires and things of that nature. So those are metals. If you go to where that staircase is and kind of go to the upper part of it, those guys are what are referred to as non-metals. And those are basically opposite of metals. Those are bad conductors of heat and electricity. They're usually dull and brittle. And actually, kind of on that staircase, as we'll talk about it when we get there, these are what are referred to as metalloids. And they're sometimes called semi-metals. And basically, you can kind of see its location. Metalloids basically will have properties that fall both like metals and properties that fall like non-metals. There's sort of that transition as you go from metals to non-metals on the periodic table. So these guys in the metalloid region will have, properties similar to metals and properties similar to non-metals, where they're sometimes referred to as semiconductors in that sort of range, because they have properties that are very similar to metals and some that, again, are very similar to non-metals. So most elements will fall into one of those three sort of categories. And again, metals are also basically these guys down here. Either metals, non-metals, or metalloids. And again, metals being good conductors of electricity, shiny, and non-metals basically being the opposite there. Any questions on that there? And we'll talk more about the periodic table in a later chapter, I think. Now, earlier we talked about elements from the periodic table. Those are things that, for the most part, come as what are referred to as being monoatomic. So most of the guys on the periodic table are what are referred to as being monoatomic. And that basically just means they come as one atom, basically, is how they naturally come. Again, those ones that I listed on the previous slide come as diatomic molecules. They come as twos. By the way, nothing on the periodic table has a charge when it is by itself. Yeah, so things only gain charges when they start combining, as we will talk about also in a later chapter. So sometimes people think they all have charges. They don't. So if you have a piece of just copper metal, it does not have a charge. So what is the definition of a molecule? So a molecule is really just the combination of two or more atoms. So to classify something as a molecule is a combination of two or more atoms. They could be the same element, they could be different elements, and those are both would be classified as molecules. So for example, H2, this is a molecule. It is also an element because it is only made up of hydrogen, so the two hydrogens together. H2O is a molecule. It is not an element. So not an element because it has hydrogen and oxygen together. So in order for it to be an element, it can only be that one thing, not an element. This is, as we'll talk about here on the next slide, it is a compound. And a compound is when you have two or more atoms of different elements together. So that is the major difference. You've got to have two or more atoms of different elements for it to be a compound. But for it to be a molecule, you simply just need 2 or more atoms together. So it doesn't matter if they're the same, doesn't matter if they're different. So both of those are examples of molecules, but only the guy on the right is actually a compound. The guy on the left is an element. And the guy on the left would not be a compound either, because obviously it has just one element involved. So sometimes people get confused, molecules, compounds, and stuff like that. Any questions on that? So that is what this definition says. A compound is a substance composed of atoms of 2 or more elements that are chemically united through some type of bonding. So for example, water, as we just saw, pretty much has 2 hydrogen atoms together with 1 oxygen atom, and they're held together by sharing of electrons, like so. And again, as we just saw, that would be both a molecule and a compound. Now, compounds you can break back apart into elements. So you can take a compound like water and you can, as we just talked about, run like an electric current over it. And it would break apart into hydrogen gas and oxygen gas, which these are both elements. And they are both actually diatomic molecules as well. But that is as far back as you could go. You can't take the hydrogen gas and oxygen gas and continue to do something to it to break it down any further. That is as far back as you go. So as I mentioned earlier, we could think about sort of the elements like the alphabet. I think there's only still 26 letters, I think. And we have dictionary full of different words. You know, dictionary used to be a book. You look up things and what things mean instead of Googling it. But, you know, Google has the thousands and thousands of words on it when you Google it. But we can make different combinations. Same thing with the elements, different combinations, different amounts of each of these elements gives us different compounds. And usually the compounds are very different than the elements that make them up. You know, for example, sodium is a metal. Chlorine naturally comes as a toxic green gas, but through the miracle of chemistry, when it comes together as sodium chloride, it's like salt, and we put it on our fries and we're okay. But you would not want to eat, obviously, the sodium metal by itself or the chlorine gas by itself either. You wouldn't get too far, I don't think. But again, very, very different properties than the elements that make it up. Carbon dioxide, which is CO2. That is a combination of carbon and oxygen, which would make it a compound and also a molecule. Again, would not be an element in this case. Obviously, hydrogen gas and oxygen gas, very different properties like explosiveness and that type of stuff compared to just water, right, which is pretty non-toxic and stuff like that. So very, very different properties of those elements that make up compounds than the compound itself. Any questions on any of that? So the next thing we're going to talk about is mixtures and pure substances. A pure substance is a form of matter that basically is composed of just basically one thing. So a pure substance, for example, could just be water. And that would be a pure substance. That's the only thing I got. We could also have sodium chloride or salt, which would be also a pure substance. Now, when we take 2 or more pure substances together and mix them, we get basically what is known as a mixture. And a mixture is really the combination of 2 or more pure substances. The important part about it is they retain their identity. So although they are mixed together, they are still retaining their identity. All the parts of the mixture are not really changing to anything different. So would that be a physical or chemical change if you make a mixture? It is a physical change. So if you think about what we did on Monday, you took some water, you took some salt, the salt dissolved in the water, you had some sand in there. That was all a mixture. You filtered out the sand, so it was still the sand. You heated off the water, which lets the water evaporate. You could have grabbed it if you wanted to, but what you were left with in your evaporating dish, if you got to that part, is just the salt left, right? So although they are mixed together, although they may look like something has reacted, it is not a chemical reaction. It's really a physical change that occurs with a mixture. Any questions on that there? Now, there are two different types of mixtures like we talked about, I think, on Monday during lab. The first type is a homogeneous mixture. And in a homogeneous mixture, with sufficient mixing, everything will pretty much dissolve, mix together. It is basically said to look the same throughout. So if you just think about maybe the salt and water part of it, that is a homogeneous mixture. When you mix the salt and water, it's going to dissolve. When you look at it, it looks just like water, right? If you ever swallowed ocean water, right? It looks like water, but it kind of tastes salty, right? So, it just looks like water. You can't see it. And that is a homogeneous mixture. Same thing if you took sugar and put it in water. If you took some sugar, it would dissolve, obviously. And if you just looked at it, it just looks like water. You can't really see the sugar. So although the sugar and the salt in those examples are not, you're not able to visually see it, they are still there. There was no reaction. It didn't really change into anything else. The other type of mixture is a heterogeneous mixture. And in a heterogeneous mixture, even with sufficient mixing, you still see different phases, you still see different layers. So if you go back to your sand in your water, you can mix that all day. The sand is never, ever going to dissolve, right? So you will still be able to see the sand in it. If you took some sand and like metal pieces and mixed it, you would still see the metal pieces in it. If you made some chocolate chip cookies correctly, you see the chocolate chips, right? It's still in there. And it's a mixture of a bunch of stuff together. So heterogeneous, even with sufficient mixing, you're still going to see the different layers. So regardless, though, of whether it is a homogeneous mixture or a heterogeneous mixture, they do retain their identity, and you can separate them out through physical means to get back the original components. So much like we did on Monday, you were able to do some physical processes to separate out those mixtures to get back the original components. So let's take a look. So one of the things that we did the other day, filtration, right? And in filtration, it's a good way to separate out, as you probably saw, a solid from a liquid. So it's a good way to separate a solid from a liquid. And you could use something like, obviously, like you did there, a funnel that has perhaps a piece of filter paper. And much like you did, you probably have something underneath that would be good. If you took your sand and water mixture, by the way, sand and water would be a heterogeneous, right? And you poured it in there, the liquid part would go through, and obviously the sand would get caught up there on the filter paper. So just by this very simple process of just basically using filter paper and funneling it or filtering it out, you're able to get back the sand. You could take the filter paper, let the sand dry out, right? And it'll be just like it was originally. Obviously, the liquid that goes through, if this was just water, would be just like the water that you had before. So by physical means here with this heterogeneous mixture, we're able to separate out both of the components of the mixture, just like they were at the beginning. Here again, nothing has fundamentally changed, which is why this is a physical change that is occurring in this case. Now, if you took something like our salt water, and our salt water is a homogeneous mixture. You could do a process if you really wanted to sort of collect everything. You could set up a process here where you have a closed situation, maybe 2 flasks, and you have this tube that connects it, and you keep the tube really cold. And you put your salt water here on one side. And if we then decide, well, I'm going to heat this. As I start to heat salt water, the water part's going to start to do what? It's going to start to, when you heat liquid water, it starts to evaporate, right? So as it starts to evaporate, it's going to create steam, right? And if it's in this container here with nowhere to go, steam's going to go this way. What happens when we have steam and we then cool it down? It goes through condensation, right? Gas back to liquid, and out on this side would drop our red water. We would continue to heat this until pretty much all the water evaporates, and the only thing we would be left with on the left-hand side here is our salt. We'll make it red salt, so you can see it, but we'll end up with just the red salt in that way. And this process, which is known as distillation, is a way that we could keep, obviously, or get back both parts of the mixture. In this case, we didn't let the water just go off into the environment, right? We were able to trap it and get it back. What you guys did on Monday, and you'll do today as well, you put it in an evaporating dish, and obviously as you heated it, the water was just lost to obviously the environment, and you were left with just the salt in the evaporating dish. But if you wanted to collect the water, you absolutely could cool it back down, and you would get the liquid water back. So on the right there is distillation, and on the left is filtration. Two physical processes that allow you to separate out any mixture, be it homogeneous or heterogeneous. Any questions? Yeah. Decanting, and basically is kind of the same idea as filtration without a filter. You basically decant, means you just pour off the liquid part. And solid. A lot of times you do something like decanting after you centrifuge it, right? So when you centrifuge a, say, test tube, if you have like a mixture of solid and liquid, what happens is like the solid gets all compiled there on the bottom, and you have the liquid part. And a lot of times the process of decanting, you just pour off the liquid part, leave the solid behind. And again, that's a physical way of separating out things. Yeah. Other questions? So why is it not a chemical change? Why does it look like perhaps the salt is gone and it went away and it reacted? It's really because we can't visually see it anymore. So when you take something like sodium chloride, it's really an ionic compound. It's really sodium ions and chloride ions together. And basically in its solid form, it is kind of packed in there pretty much tight together, all those ions. And then a really important thing in chemistry is the idea of opposites attract. So things that are positive and negative are attracted to each other. Things that have the same charge, things that are negative and negative, they don't want to be near each other. They repel each other. Things that are positive and positive do not want to be near each other either. So really that positive negative attraction is something that brings things together. So negative, negative, positive, positive, they repel each other. So when we take something like water, water actually has charges, and we'll talk about it. It's what's referred to as being a polar molecule. The oxygen side of water is more negative. The hydrogen side is more positive. So what happens when we dissolve something like salt in water, the water molecules basically go in, pluck off some of these ions. And what happens is the sodium ion gets surrounded by the negative side of water, which is the oxygen. And what happens to the chloride part, which is the negatively charged guy, it gets attracted to the positive side of water. So the hydrogens are more attracted to it. And that is what keeps that really strong attractive force of the sodium ion and the chloride ion apart from each other, basically, right? They get surrounded by a bunch of water molecules. That also makes it visually, we can't see it anymore. It's like gone. It's all trapped in the matrix. We could again re-see it like you saw, because when we start heating this, the water will start to evaporate, right? and these guys will eventually all evaporate. And then what happens is these two guys have nobody in their way. They're going to come back together to make sodium chloride, and your solid reappears. So that's why it kind of looks like it goes away. And then when you heat it, the water molecules escape. And now there's nothing to prevent those really strong attraction, be the positive guy and negative guy, to come back together. And that's when the solid basically reappears. Any questions on that? By the way, when we do dissolve something, we oftentimes do what? Stir it, right? Adding energy, right? Also throwing a bunch of water molecules all over this. So a bunch of them get guys. And that's how they're able to kind of pry them apart and surround them. We have that energy that's needed by stirring, and also putting a lot more water all over the place that allows those guys to be plucked off. Any questions on that? So as we talked about, those are two ways to separate out a mixture. What I bad drawing on the right there was distillation, and filtration, obviously, we used there before. So distillation is a really good way to separate out a homogeneous mixture where you can't really see the different components. We're basically using, in the process of distillation, we're using the differences in melting points and boiling points, basically, really boiling points. So here we basically have two things. We have water, and we have the ionic compound or the salt. And earlier we were talking about that the strength of the forces that hold a molecule together results in either a lower boiling point or higher boiling point. In comparison, water has actually a much lower boiling point than the ionic compound. The ionic compound is held together very strongly. Most ionic compounds will never boil. That's how strong they're held together. You could heat the heck out of it. It will not boil. So because water actually boils first, we're able to boil the water and basically get the water away from the ionic compound. And that again allows the ionic compound to come back together. So the process of distillation is using really some differences in physical properties like boiling points to allow you to separate out the mixture. And clearly this picture looks exactly like my award-winning art that I drew earlier, but that's probably a prettier picture, I suppose, of distillation. Question on mixtures, way to separate out mixtures, compounds, elements, states. All right, that is chapter 3. Yes.